Hello, we're going to take a look at passing the Riemann sum function and passing functions as a parameter. Just recall from your calculus that the area under a curve, call it f of x, as you see in this diagram, can be approximated with many rectangles. And we can under-approximate and we can over-approximate. You can review that later. But what we're going to do is we're going to build a bunch of rectangles. Each one will have a base of delta x of width, and the height will vary depending on x. And x will start from variable value a, and go all the way to some value b plus some delta. There's a little delta x here. And we supply f of x, so it gives us a value of y. We take that y, times it by our delta x, and we get the first area. We move over from a, we add a delta x. Now we're in this, at this point, supply a plus delta x, and it gives us a new y value, which is this new height, times delta x. And we repeat that process. To build this in software, we could use a for loop, a do while loop, or a while loop. I chose a while loop here. And I want to create clean code. I think clean code is pretty important. You can go online and look up Riemann sums, C++ code, and judge which is cleaner. So here I'm going to look at a couple of functions. I'll call one function g. And it takes one variable x and returns a value. And I'm using the power function. And I'll have another function, I'll call it f, and it's very simple, of 2x. Next, I'm going to actually sum up my function. If you look down here at the center of the screen, you'll see I have an f of x, whatever it is, or g of x. I'll make this generic in a moment. Right now it's only working with f of x. Give me some starting position, times it by my width as my delta x, and add these things up and move along to get my new x. Notice each new x is just a delta x over. If we go back a couple of slides, we see we're just moving over delta x's, delta x's, delta x's until we hit the end of the row. So over here you say continue doing this, starting at some x at a. Keep moving over as long as x hasn't reached the end of the line, say b. And we have an initialization for delta x. Delta x says, tell me what a and b are, and how many ways do you want to slice it up? That'll give me each of my delta x's. Next, I want to encapsulate that whole thing. Go back a slide. This whole piece of code is going to be encapsulated in a function called area. And here's my f of x. And what I want to do is have this work with any function that matches the pattern, one double going in and a double coming out. And that's what this f here is. This is now a variable. Notice there's a star next to it and parentheses around that, which indicates it is an address of a function that accepts a double, has a parameter, and returns a double. And then I have three other parameters: a, the starting point, b, the ending point, and how many intervals to slice this up into. And the whole thing has a beginning and an end, and it's nicely wrapped in a function I called area. You could have called it integral. Well, here will be our prototypes, our functions f and g, and our function area. Notice how messy this looks. Double, star, double. Not very clean looking. And I did something nice over here. I said, let's have a default of 100,000 intervals. However, that really wasn't very nice to look at. So I took advantage of this keyword called type def, and it says, instead of creating a variable, create a type called fun, as in function, and functions are fun, that accepts a double and returns a double. So now fun is not a variable anymore, it's a data type. So notice over here in the prototype for area, I replaced it with fun. Since I replaced it with fun, I now have cleaner looking code. The area, fun. My function f is fun. Admire how clean it is. Look down here. This is not a regular, it's not f, it's any function. Here's an application of it. Doubles a, b, and sum. I have a set to 0, b set to 10. And now I call my area with f, the function f, a real function f. Go all the way back. Here it is. There's function f, which is just 2x, and you also notice function g. Keep that in mind. I'm going to use that later. So I say, here's a function f. There's a and b. It goes inside and magically comes out with some sum. I can repeat those steps, change a and b, and now give it the function g. And if I really like, I could say I want g to be that sum to be over 500,000 intervals. And so I just add the last parameter. Here's a complete look at what what the program would look like. You should probably type this in manually. I also included inline here to give the compiler the option to actually take this code 2x time 2 times x and place it in here when it's being used. That's probably not going to happen, but it's a nice exposure to the word inline. Here are some reference materials, including a previous video from a classroom discussion that calculated the derivative using functions as parameters. Thank you.